So how do we go about it? Just like any other test, you're going to have to state your null and your alternative. You're going to have to actually calculate your F statistics. You're going to have a critical value, which you will obtain using your alpha level and your degrees of freedom. And then you're going to be comparing your critical value to the F ratio, and the one who is most extreme wins. So if your F ratio is more extreme than your critical value, that means you're rejecting the null. If your critical value is more extreme than your F ratio, then you fail to reject the null and you make your final conclusion. So let's go ahead and look at our example again. So Dwight here needs to go through that list. So first of all, let's go ahead and identify our hypothesis. So in the previous test, if you remember, we had to worry whether our test was directional or non-directional. Guess what? An ANOVA is always going to be a non-directional test, okay? Because we're testing differences between three groups, okay? So as I said at the very beginning, the ANOVA simply tests for differences, but it does not tell you which group differs from each other. So we're never going to have a direction. And as you can see here, when you read the word problem, it says we're looking to see which one sells a significantly different amount, different, not a particular. It doesn't say that the Scranton is going to be selling more or the Albany. We're simply looking for differences. And there is a special name for that. So when a test is a non-directional test, that means it's an omnibus test, okay? So this is a new term for you. Make sure you know what omnibus means, just in case you see it on an upcoming final exam. Okay, so that means that it has no particular direction, okay? It's a non-directional test. This is how I want you to write, to state your null and your alternative. So anytime you're running an ANOVA, and what I want you to be pay attention to is the difference between the null and the alternative. As you notice here, in the null, I use mu instead of x bar. Okay, so assuming that we do know what are the population parameters, okay, we're going to state that as always we do that the null states no differences. So that means that the mean of the population number one is equal to the mean of the population number two and equal to population number three. So there's essentially no differences between the means of those three populations. On the alternative hypothesis, right, we collect data from samples. So this, you can imagine the Scranton would be sample number one, Albany number two, and Akron would be number three, right? So we're going to be, that's going to be my X bar, right? So, and since we're trying to prove that there are differences between those two groups, but we do not know which group differs from which, we're simply going to say that X bar number one is not equal to X bar number two or is not equal to X bar number three. So we identified our hypothesis. The next step would be to actually calculate our F ratio. As always, we're also going to use a p-value of 0.05. That means we're only willing to risk 5% and we want to be 95% sure that the results we obtain are not due to chance, right? So how do we go about it? I will always give you SSB and SSW or MSB or MSW. The thing that you need to pay attention here, if I do give you the MSB, apparently you're not going to have to divide with a k minus 1 because MSB is equal to this whole thing. Okay, so pay attention to what I'm giving you and use the appropriate formula. So in this particular case, I'm giving you the SSB and I'm telling you it's 400. Your SSW is 540. And let's see what is your N and your K. Okay. So this is the data that you're having. So might be giving you something like that. And you know that you're having one, two, three branches, right? So these are your number of groups. And then in every branch, you're having one, two, three, four, five participants. That means 5 plus 5 plus 5, that is 15. Your total N is 15, and your K is going to be 3. Now we have all the information we need to actually calculate our F statistics. So let's go ahead and plug in our numbers, and we end up getting an F statistics all equal to 4.44. The next question is this F value large enough to reject the null? Dwight is happy. He knows that the larger the F value is, the more likely you're going to be rejecting that null. So let's see, we're going to need to actually find our critical value. P equal to 0.05. We also going to need degrees of freedom. Now this is your new F table. You can find this on the back of your book, and I will also post it on Titanium. And here the way you read this is you can see here that you're having degrees of freedom for the numerator. That is that k minus 1. And degrees of freedom for the denominator, that is going to be your n minus k. And here you have the different alpha levels. So depending on the kind of degrees of freedom you're having, you're always going to have the choice between an alpha of 0.01, 0.05, or 0.010. Okay, so degrees of freedom for numerator, denominator. Now let's put it all together. So if you remember, we had three groups. Minus 1 leaves us with 2. So your numerator degrees of freedom are 2. Okay, you find it there. Your total n was 15 minus the three groups. That leaves you with 12. Okay, let's locate 12 in our table. And we have an alpha of 0.05, which is right there. And that means our critical value is going to be 3.89. Let's compare our critical value now to our F ratio, which is equal to 4.44. Clearly, we can see that 4.4 is way more extreme than 3.89, which means what? Okay, we got significant results. We can reject the null. So the conclusion is that there's significant differences between the three branches. Okay, Dwight is really happy, but we're going to have to say goodbye to him because the next step is you would need to find, after you conclude your ANOVA, you need to find, well, I found those differences. The question is now which group differs from which one. So goodbye, Dwight, and we're going to go over to the ANOVA and SPSS. As I said before, I'm not going to actually open SPSS here. I just want to show you the steps. It's really, really easy. Just literally follow what I'm showing you here. The data set that you're going to be using for this example, you can find it on Titanium. Okay, if you want to use it and just play with it, experiment, you're more than welcome to do so. But it's very, very easy. Okay, so this particular data set compares three different cities on standardized test scores between first and third graders, okay, in its single town. And we want to see if there's significant differences between those three towns. So this is what your data looks like. And the way you run an ANOVA is like always, you're going to be going to your Analyze menu, compare means. You're going to be scrolling down to one-way ANOVA. As you can see here, you also have your t-test that you did on the previous inferential test, but this time we're going to be selecting the one-way ANOVA. You're going to see a pop-up window just like this, and you need to fill out these boxes here. So you have the dependent list. This is where your dependent variable goes. In this particular case, my dependent variable is going to be the standardized tests. And then the factoring is going to be the different cities, Owatonna, so on and so forth. And then you have all these different options here, which I will explain. So go ahead and you place, by clicking this little button here, the variables to the right area. So once you do that, the next thing that I would like you to do is select the options button. And what that gives you is actually the option of running descriptives together. So you do not have to go and run separately descriptive statistics. You can just click it right here and SPSS will automatically do this for you. The next thing that we're going to do is actually run a post hoc test. And this is the new concept that I told you about. So post hoc means after the fact test. So you only run a post hoc test if you obtain significant results in your ANOVA. Of course, if you do it manually, that's would be the deal. SPSS will run it for you no matter what. Uh, but if you see a question such as, do you need to run a post hoc if your ANOVA is not significant? The question would be no, because you only run a post hoc if your ANOVA is significant. If not, then you do not need to run because it means there's no differences between the groups, so why bother running a post hoc? So in the SPSS, you're gonna click the post hoc button here, and it's going to give you all these different choices. Okay, the most two popular ones I would say is the Bonferroni and the Tukey. In this class, we're just going to stick with the Tukey. You do not need to use the Bonferroni. Bonferroni is very similar, just a little bit more strict when it comes to how it compares the differences between the groups. It kind of like penalizes them more, more degrees of freedom, and so on and so forth. Um, so once you click that, you click continue, and then eventually you're going to get that output that I'm talking about. But before we get into the outputs, let's just talk a little bit more about the Tukey test. So first of all, it's a Tukey, not a turkey, okay? And it's a post hoc test, after the fact test. And the best way to explain it, you're not going to solve it by hand, as I said, is try to imagine is running multiple t-tests between the different groups. So in this particular case, we're having three different cities. So you're going to be comparing city number one with city number two, city number one with city number three, and then city number two with city number three. So SPSS automatically runs all these multiple t-tests, and then from there, you can see which one significantly differs from the other. So let's see the output. So the moment you run Anova, this is the full output you're going to be getting. Now let's take a look a little bit closer. So this is going to be your descriptive tables, right? So this is just what you know, like what describes your different variables. So apparently here you're having three cities, Owatonna, Red Wing, and Mankato. Okay, here you can see their size. Owatonna has 16 participants, Red Wing 18, Mankato 16, so your total N is 50. Right here you can see your mean scores for the standardized tests. So for Owatonna, it's 72.3, Red Wing 83, Mankato 93, and so on. You get your standard deviation, and it's pretty cool. That gives you the confidence intervals. Now this is your meat and potatoes here. So this is your ANOVA output. As you can see, it states ANOVA right on top, so you cannot be confused. And this is when you're going to actually be reading to see, to obtain your F value first of all, and also if your ANOVA is significant or not. What I want to go over is, you see here it says sum of squares, so this is going to be your SSB, right, between group differences, and your SSW, your degrees of freedom, and this is your MSB and your MSW. Remember that you're comparing three cities, so it's three groups minus one, two, so that's why your DFs for the numerator is 2. Your total participants were 50 minus the three cities, the three groups, right? That leaves you with 47. So your degrees of freedom here is going to be 2 and 47. Um, this is your SSB, as I said before, which if you divide it with your degrees of freedom, you're going to be getting your MS. Okay, and this is your total F value. So this is your F statistics, and this is your significant level. So apparently here, your significant level is 0.000, which is very, very significant because it is way less than 0.05. So since it's less than 0.05, that means you obtain significant results and you can reject the null. The way you would actually state those results would be F parenthesis 2 comma 47 close parenthesis equal to 756.12 right here, comma, P less than 0.05. That means that you got significant results. Finally, the last output that we're going to be getting is the multiple comparisons for the Tukey test that we run, the post hoc test. And this is exactly how, as I told you, it runs a bunch of little t-tests. So it will be comparing the Owatonna with Red Wing, Owatonna with Mankato, Red Wing with Owatonna, Red Wing with Mankato, so on and so forth. So remember t-test formula, x bar 1 minus x bar 2. So right here would be the mean of Owatonna minus the mean of Red Wing, and this is the difference of their means, right? And you get a significant level of 0.00, very significant. So apparently there is a significant difference between Owatonna and Red Wing. Likewise, when we compare Owatonna with Mankato, we see that the differences between their two means is 20.68750, and you also obtain very significant results. Here, pay attention that this is the same value as this. The only difference is that here you have a negative side and here you have a positive. Well, think about it. Here you're comparing Owatonna with Red Wing. Here, Red Wing versus Owatonna. So if this is your x1, that means x bar 1 minus x bar 2. Here you're having x bar 2 minus x bar 1. And that's why you kind of like reverse the sign here, because you're subtracting the mean of town number 2 from town number 1. And here's town number 1 minus town number 2. Okay, so all you need to read here is Owatonna Red Wing, Owatonna Mankato, and would be also Mankato with, I guess, which one is left with Red Wing. Okay, so that would be your only other comparison that you need to look. And since your significant level here is all zero point 0.00, that means there are significant differences between all three cities. Okay, not just two of them. That means Owatonna is very different than the Red Wing, and Mankato is very different than Red Wing, and Mankato is very different than Owatonna. Okay, so this is how you read the multiple comparisons table. Hopefully this was not very hard. If you have any questions, feel free to email me, or you can ask me whatever you like when I see you on Friday. Have a good one. Bye-bye.